Okay, so this is a lightning talk, so no worries. Thank you for staying. Yeah, we'll be talking about topology awareness in schedulers. My name is Dimitri. I work at Nvidia. My team builds tools and services to make Nvidia digital cloud robust and effective. I'm also a contributor to open source projects like Navigator and Topograph, and I'll be talking about Topograph today. Just to describe the problem that I'm trying to solve. So AI models are becoming more complex, and that requires more resources and compute power. And that in turn brings a cluster to be more contain more GPUs, more computes, but at the same time, AI and HPC workloads, they have their requirements. For example, if you're running a training job, a distributed training job, that jobs, they exchange vast amount of data, so they have to be to run in very high bandwidth. Or if you run inference job, it's split in the microservices, so the requirement is to have very low latency. And as GPU becomes more powerful, also the other hardware components like networking is also becoming more stronger. And for example, Nvidia GPUs, racks, they developed technology that allows unblocking communication between between any pair of GPUs at high speed. That's called NVLink technology, and that's deployed inside the rack. And besides, if you're connecting,
hold the mic a bit closer. It's a little bit hard to.
Sorry. And if you're connecting racks, so you can use a InfiniBand. It's also a relatively new technology. So the problem here is when you have a distributed workload that placed randomly on your cluster, you might the latency becomes a bottleneck because for obvious reasons, like to go from one node to another across through all these switches, it will take time, and that time is very valuable, especially for AI and HPC workloads. So if we can place the jobs, let's say, on a single rack, then we will get a bandwidth of 1.8 terabyte per second. If that's not possible, like if your workload is bigger than one rack, then we can place them on two racks that have only one switch in between them, and then we can enjoy that minimal network between every node, and so on. So the good news is that there are schedulers that can allow you to do such topology-aware placement, but there are also challenges. So for scheduler by itself cannot understand topology, so there should be a tool that helps with that. And also, if you're running in cloud environment, you don't have not necessarily have the access to all information about topology. So this problem is what Topograph is trying to solve. Topograph is an open source project, and it discovers and maintains cluster network topology in CSPs and on premises. It supports Slurm, Kubernetes, and hybrid Slurm and Kubernetes clusters, Today it can run in AWS, OCI, GCP, and Nebius clouds. For on-prem, we support clusters based on InfiniBand and Spectrum-X network cards. And for specific environment, we can leverage DRA. It stands for Dynamic Resource Allocation. It's a new concept in Kubernetes. So let's talk about workload managers. Anybody familiar with Slurm? Oh, good. 3 people. So Slurm stands for Simple Linux Utility for Resource Management. It is very old system, like 20 plus years. It has very large user base, and especially for HPC workloads. It's used in for research, in government, in industry, and it has been, like I said, has been for a very long time. It has implemented topology-aware scheduling from the very beginning, and that was the main goal of this workload manager. So next, Kubernetes. I assume everybody knows that. It's a container orchestration platform, and it recently became, with the advent of AI, it became very popular to run AI workloads in Kubernetes. The downside until a few years ago was that it didn't support topology-aware scheduling, and especially gang scheduling. When if you have multi-node workload, you want all pods to run at the same time. So if you cannot, for example, deploy one of the pods, then there is no reason for the entire workload to run. That functionality has been added in the past 2 years. There are several scheduler systems. Some of them developed in Nvidia, some of them developed by Google, for example, Q, if I'm not mistaken. So now Kubernetes is very well positioned in the area of multi-node AI workloads. And the last one is Slinky. Slinky is a hybrid between Slurm and Kubernetes. So Slurm, by definition, is deployed on bare metal or virtual machines. It's a stable environment, but it has problems if you want to scale up. For example, for a specific amount of time, it's very difficult to do because your infrastructure is more or less static. So Kubernetes solves that problem, especially in cloud environment, but we cannot run Slurm in Kubernetes, or we could not. So the idea of Project Slinky is to use Kubernetes infrastructure and to let Slurm users to run Slurm application natively. So this is very young project, introduced in 2024, released in 2025, and has basically it is getting momentum in AI and HPC. Just a few words about how topology is provided to Slurm and Slinky. So this is a simple example of a cluster. So you can see backend switch fabric, three tiers, and we also have racks with nodes, and that sign tells that it's a NVLink domain. So all nodes in rack can talk between each other. So in Slurm can ingest topology in 2 formats, tree and block. tree format follows the backend switch fabric, and block format basically follows the NVLink domains in the racks. I think last year, Slurm introduced new format. It's called YAML format for pair partition topology. What it means is in your cluster, if you have, especially when you have heterogeneous cluster with different type of node pools, you might decide that for specific set of nodes, you want to use specific topology. So if you have GPU partition, you can use block topology, and for CPU partition, block topology doesn't make sense, so you use tree topology. So that format will allow this division. In Kubernetes, Topograph applies node labels that combines basically combines both block and tree topology that we saw in Slurm. From the high level, Topograph has 5 components. The API server exposes REST API endpoint and handles topology requests. Provider implements specific API client if we are talking to CSP, or it uses tools from bare metal or virtual machines. So provider gets the basically provider is the model that discovers network topology and represents it in an internal way, and engine reads that and generates output in the format that workload manager expects. For example, for Slurm and Slinky, it will generate topology config. For Kubernetes, it will label the nodes. There are 2 additional components, node observer and node data broker. Those components deployed in Kubernetes. Node observer will tell API server that something changed in the cluster, if node got added or deleted or it became unhealthy. And node data broker works in tandem with provider to get specific CSP-specific information into node annotation that will be later used by the algorithm. One feature that Topograph has is graph reduction. So when we are talking to CSPs, when we are using CSP API, they return topology in simplified way, usually in 3 tiers, in the tree format. But if your deployment runs in on-prem cluster, you will have redundancy. You will have multiple switches. So Topograph can translate that into tree representation. And that is important feature because when topology is sent to scheduler will use it, read it as a graph, and will parse the graph to find the optimal set of nodes. So the simplest the graph, the faster scheduler can do it works. So that actually improves the performance of scheduler. Yes, obviously benefits of using Topograph is that without changing your cluster, it will help scheduler to better leverage, to better utilize GPU and networking. It will reduce latency. You will and that in turn will help you to avoid effect of noisy neighbor, because all workloads will run in a localized network environment. So that's it. Yeah.
hold on to that question.
I can just talk loud. So you're doing auto discovery. So we used to just use HW lock to do discovery or lock info, and then we do our own either MP run or S runs for doing the cluster. What are you doing to actually discover the capabilities? Is it both CPU, GPU, memory, and interconnect speeds?
Okay. So for CSPs, so we need to differentiate between CSPs and on-prem.
Right.
For CSPs, we are using API, internal API of CSP. So they do not provide information about bandwidth yet. Because Topograph has that abstraction level, then for on-prem, we also currently disregard that information, only focusing on actual network topology. There is a future plans. We can also use information about. We can not only build graphs based on topology, network topology. We can build graphs based on power topology. So it's all kind of it's evolving project. It has been around for only a year and a half. So lots of ideas. And actually, if you have ideas.
Are you doing runtime validation? Because often we discovered that the topographies that when we were spitting them out, they would be inaccurate, or we would discover topographic errors where, for example, an interconnect would be rated at a speed, but when we would run a job, it wouldn't actually run at that job. So are you doing, synthetic jobs to do speed tests?
No, we don't. No. Not yet. Yeah. Thank you. I can see the question over there.
I have a question about my guess is that your topography software is kind of probing the topography of the current network you have in place, and you kind of go through the current topology and try to find some loops and try to find some redundancies and try to simplify. Is that correct?
It's one of the users.
One of the users.
Yeah, when you have your cluster on-prem, the usual architecture is a closed network, right? When you have multiple redundancies, you have multiple switches. So what Topograph does, it finds the group of switches that has the same characteristic and same connectivity, and presents it as one node.
Okay, and so my question is once you run a certain component, call that CSP or whatever is the name of the API, and you determine the right topology, the most simple one that is the most useful, can you use that software of yours to apply that new configuration so that, because essentially, all these switches, they have some physical wiring and all that stuff, right? And so now I'm kind of curious, can you, after you find out what's the best topology, can you reinforce with your software?
So that simplified topology is sent to scheduler. Scheduler takes it as a source of truth.
So essentially, the other component of this one can actually do that, and you can actually do. And so it's all programmatically, right? So
no,
excellent. Thank you.
Okay, thank you for staying late.